Simplify 2 times k to the fourth times 4 times k. Let's do this. Let's separate the 2 and the 4. So 2 times 4, kind of scooch that over there, and put the k's over here. Let's kind of split them up. Okay, k to the fourth times k. Now 2 times 4 is 8. Don't overthink it. K to the fourth times k, if I wanted to, I can make that an invisible 1. Now the reason why I'm doing this is there's a rule that says when you multiply terms of the same base, all you have to do is add the exponents. So k to the fourth times k to the first is k to the fifth. So at the end of the day, 2k to the fourth times 4k is 8k to the fifth. And we're done. Simplify 4 times v to the third times v times u squared. Let's kind of split all of these up the best that we can. 4 is 4. It's on an island all by itself over there. Then you have v to the third times v. So let's keep those separated like that Offspring song. And then we have u squared all by itself. Right there. Now, what you're supposed to do is if you have like terms, and you have to simplify them, simplify them. 4 is kind of alone, so we'll leave 4 like this. Now, when we multiply terms of the same base, so v cubed times v, what you're supposed to do is add the exponents. And you might be looking at this guy and saying, what exponent? Well, it's an invisible 1. So if I multiply 3 v's times another v, I get 3 plus 1, which is 4 v's. That u squared is all alone, so u squared is all alone. So at the end of the day, 4v cubed times v u squared is 4v to the fourth times u squared. And really the only things that changed were the v's because there were more than one v and everything else was all alone all by itself. Simplify 4r to the negative third times 2r squared. All right, this is what I want to do first. I want to split up these numbers on their own thing. So I'll put 4 times 2 completely on its own. Then I'm going to take r to the negative third, write that over here, and r squared and write that over here. Now, what we have in this problem is a negative exponent. When you have a negative exponent, you move it to the other side of the fraction bar and make it positive. Now you might be saying, fraction bar? What fraction bar? Well, there is none. So if I wanted to, I can make this over invisible 1. So I did. So you go through all of these, and if it has a negative exponent, you move it to the other side. Or if it has a invisible 1 exponent, or if it's positive, you leave it where it is. So 4 stays. 2 stays. That r to the negative 3 moves to the denominator and becomes r to the positive 3. That r squared stays. And then you simplify what you can. 4 times 2 is 8. Don't lose sleep over it. Now, if you have a term dividing by another term, what you do is you figure out which one's more powerful. In this case, the denominator has more r's than the numerator. So you subtract the exponents and keep it where it's more powerful. So 3 minus 2 is 1. Leave it in the denominator. And of course that looks kind of sloppy, so I'll just write that out as 8 over r. So that's how you do it. Simplify 4a to the third b squared times 3a to the negative fourth b to the negative third. All right, this is what I'm going to do. I'm going to move all the like terms together. So 4 times 3, you're now hanging out. A cubed times a to the negative fourth, a to the third, a to the negative fourth, you're all hanging out. And all these b's, you're all hanging out together. Is that step necessary? Nah. But was it that difficult? Nah. Now, I see negative exponents. Okay? When you see negative exponents, you're going to move them to the other side of the fraction bar. And you might be thinking, whoa, 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 whoa. I don't see a fraction bar. No, you don't. So I'm going to create one and put everything over 1. Now we take our time right? I'm going to rewrite the fraction bar, and we look at all 6 of these items, 4, 3, a cubed, a to the negative fourth, b squared, b to the negative third, and we see if they stay or if they move. If it has a positive exponent or an invisible 1 for an exponent, they stay. So 4 stays, 3 stays, a to the third stays, a to the negative fourth moves to the other side of the fraction bar and becomes positive. B squared stays, and b to the negative third moves to the other side of the fraction bar and becomes positive. Now we simplify. 4 times 3 is 12. If you're dividing terms of the same base, subtract the exponent and keep it where it's more powerful. Now, what I mean by more powerful is a to the fourth is more powerful than a to the third, and that exists in the denominator. So you're going to do 4 minus 3 and keep it on the bottom. Same thing with the b's. There's 3 b's on the bottom, 2 b's on the top, so the denominator is going to keep the b, and 3 minus 2 is 1. Now that looks sloppy. You don't need 1s for exponents, so let's wrap this up by saying 12 over a to the first, which is just a, b to the first, which is b, and that's going to be my answer. Simplify parentheses to the 0th power, where inside the parentheses you have x squared. Well, if I'm going to take a parentheses to the 0th power, it doesn't matter what's inside it. Anything to the 0th power is 1. Anything to the 0th power is 1. So a parentheses that contains x squared to the 0th power is just 1. Don't overthink it. There's nothing to overthink. The answer's 1. Done. Simplify 2x squared in parentheses to the negative 4th power. All right, when you take a parentheses and take that to an exponent, what you do is you distribute that exponent to everything, and you multiply that exponent to these exponents. And you might be thinking, whoa, 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 whoa. 2 doesn't have an exponent. Yes, it does. It's invisible 1. So when you take a power to a power, you multiply the exponents. So you're going to do 1 times negative 4, so 2 to the negative 4, and 2 times negative 4, which is 2 to the I'm sorry, not 2 to the negative 4. Yeah, 2 times negative 4, which is x to the negative 8. Now, both of these have negative exponents. When you have negative exponents, you move them to the other side of a fraction bar. And you might be thinking, there is no fraction bar. Nope, so let's make one. So now that we made ourselves a fraction bar, 2 to the negative 4th becomes 2 to the positive 4th on the bottom, and x to the negative 8th becomes x to the regular 8th on the bottom. And since we're left with nothing up top, leave it as a 1. Now, that might be good for many teachers. Some teachers might want you to say, all right, well then what's 2 times 2 times 2 times 2? 16. So maybe this is another possible way that you can answer this. Either one is technically correct, but in this case, that is what you get when you simplify. Simplify 3n to the 4th over 3n to the 3rd. All right, so if I am dividing terms, right? If it's a number over itself, cross them out, just get rid of it, easy peasy. That leaves us with n to the 4th over n to the 3rd. Now, if dividing terms of the same base, what you do is you figure out which side of the fraction bar is more powerful and leave your letter there. N to the 4th is bigger than n to the 3rd, so n's going to stay up here. And when you're dividing terms of the same base, once you figure that out, subtract the exponents. 4 minus 3 is 1. So we end up with n to the 1st over 1, which looks just sloppy. So n to the 1st is just regular n, over 1 is unnecessary, so you end up with just n. M to the 4th over 2m to the 4th. Now, we are dividing terms. If when dividing terms you have something in the numerator that's literally the exact same thing as something in the denominator, and all you're doing is multiplying upstairs and downstairs, get rid of them. So when you completely eliminate a numerator, you're left with 1. And since all I have here is 2, you're left with 2. Nothing else can be done. That's it. That's the problem. Don't overthink it. Simplify 2x to the 4th, y to the negative 4, z to the negative 3rd, all over 3x squared y to the negative third, z to the fourth. All right, big fraction bar. Whenever you see positive and negative exponents in fraction bars, the first thing you're going to think is, all right, I have 1, 2, 3, 4, 5, 6, 7, 8 items. Which of them move and which of them stay? Things that have an invisible 1 exponent or a positive exponent stays. Things that have a negative exponent moves to the other side of the fraction bar and becomes positive. So 2 stays. X to the fourth stays. Those are both positive exponents. Okay? Y to the negative fourth is going to move to the denominator and become y to the positive fourth. Z to the negative third is going to move to the denominator and become z to the positive third. Our numerator is completely done. Now let's go down here. 3 stays. X squared stays. Y to the negative third is going to move to the numerator and become y to the positive third. Z to the fourth is going to also move. Oh no, z to the fourth is going to stay. Oh, silly me. So let's do this. Let's regroup things where things are kind of aligned nicely. Okay, I'll put the 2 over here. I'll put the 3 down there. I'll put the x to the fourth right here. I'll put the x squared directly underneath it. I'll put the y to the third right here. I'll put the y to the fourth directly underneath that. And then we have z to the third, z to the fourth. That step, not necessary, but what it does is it cleans things up. Now we are going to simplify the best that we can. 2 over 3 is 2 over 3. There's nothing that you can do there. When you're dividing terms of the same base, you figure out which one's more powerful, leave the letter there, and then subtract the exponents. So x to the fourth over x squared has x to the fourth more powerful in the numerator. Leave x up there. 4 minus 2 is 2, x squared in the numerator. I have y to the third over y to the fourth. Y to the fourth is more powerful. Leave it in the denominator. 4 minus 3 is 1. I'll clean that up in a little bit. Now when they're next to each other, when multiplying terms of the same base, all you have to do is just add the exponents. So 3 plus 4 is 7. So z to the 7th power. So cleaning this up just a little bit, I have 2x squared in the numerator, 3y to the invisible 1, z to the 7th in the denominator. Fun stuff. Simplify 3x cubed, y to the negative 1, z to the negative 1, all over x to the negative 4, y to the 0th, z to the 0th. All right, so I have a big fraction bar, and what I'm looking at is positive exponents, negative exponents, and 0 exponents. We're going to take turns going through all 1, 2, 3, 4, 5, 6, 7 of these terms and seeing if they stay, seeing if they move, or seeing if they turn into anything. Anything with a positive exponent or an invisible 1 exponent stays. So 3 stays at 3. X to the positive 3 stays in the numerator. Y to the negative 1 moves to the denominator and becomes y to the positive 1. Z to the negative 1 moves to the other side of the fraction bar and becomes z to the positive 1. So we're done with the numerator. Now let's go down here to the denominator. X to the negative 4 becomes x to the positive 4 in the numerator. Anything to the 0th power becomes 1, so times 1. Z again to the 0th power becomes 1, so times 1. So let's rearrange things and maybe clean things up a little bit. All right, 3 times x to the third times x to the fourth, not going to do much there. Y to the invisible 1, z to the invisible 1, times 1 times 1. If I multiply 1, nothing changes, so I really don't need them. Now, 3 doesn't change. If I multiply terms of the same base, add the exponent. X to the third times x to the fourth means I add the exponents, and that becomes x to the 7th. Y to the first doesn't combine with anything, and I don't need that invisible 1 there, so leave it as y. Z to the first also doesn't combine with anything, and I also don't need that invisible 1 there, so leave it as just z, and this guy becomes 3x to the 7th all over yz. Simplify x to the fourth in parentheses to the negative third power times 2x to the fourth. First thing that we're going to do is whenever you see a parentheses with a power in it taken to an exponent, you're going to want to multiply those exponents. So 4 times negative 3 becomes x to the negative 12. Right next to that we have times 2 times x to the fourth. Now when I see these guys, what I like to do is I like to group things next to each other. So 2 is kind of on an island all by itself. And then I'll move the x's next to each other. So I have times x to the negative 12 times x to the fourth. Now whenever you see a negative exponent, what you're supposed to do is move it to the other side of the fraction bar and make the exponent positive. Now you might be looking at this and saying, there is no fraction bar. You're right. So make one. Put it over 1. So now what we do is we go through each term and we say, do you stay or do you move to the other side? If it has a positive exponent, then it stays. If it has a negative exponent, then it moves to the other side and becomes positive. So 2 stays up here in the numerator and stays 2. X to the negative 12 moves to the denominator and becomes x to the positive 12. And x to the fourth stays up here in the numerator. Now, when you divide fractions of the same base, right? When you divide terms of the same base, what you do is you figure out which one's more powerful. First things first, 2 doesn't move. There's nothing like it. Leave it there. When you divide terms of the same base, figure out which one's more powerful. The denominator is more powerful, so leave the x down there. Then what you do is you subtract the exponents. 12 minus 4 is 8. So if I have 4x's on the numerator, 12x's in the denominator, I end up with 8x's in the denominator. Let me write this out to make it look a little bit cleaner. So I have 2 over x to the 8th, and that's my guy. Simplify 2 times y to the third times 3 times x times y to the third all over 3 times x squared times y to the fourth. Well, I have a big fraction and I'm multiplying a bunch of stuff with powers and numbers and yada yada yada. What I like to do is I like to move all of the common things near each other. So 2 times 3 all over 3. Okay. What else? I have, let's go in alphabetical order. X over here, put x there, x squared on the bottom. Okay, y to the third next to y to the third, all over y to the fourth. Now, before we go any further, a fun little fact is since all we're doing is multiplying across the top and multiplying across the bottom, anything that's exactly the same upstairs and downstairs is allowed to cancel each other out. So I'm left with 2 times x times y to the third times y to the third over x squared times y to the fourth. Now I have several things going on here. Several. Since I have 2 y's up here next to each other, let's combine them. So nothing happens with 2, nothing happens with x. But since I have y to the third times y to the third, when you multiply terms of the same base, add the exponents. So you become y to the sixth. That's going to be over x squared, y to the fourth. Okay, let's simplify some more. 2 is just 2, nothing happens. When you divide terms of the same base, figure out which side is more powerful. The denominator in this case has one more x than the numerator. That's an invisible 1. So you keep the x in the denominator, subtract the exponents, 2 minus 1 is 1, and put the 1 right there. Do the same thing with the y. Y to the 6th in the numerator, y to the 4th in the denominator. The numerator is more powerful. By how many? 6 minus 4 is 2. So everything is simplified. Let me just clean this up. 2y squared over x to the first. I don't need that 1. It's just going to be x. Simplify 2m to the negative fourth all over parentheses 2m to the negative fourth cubed. I'm going to approach this one in a completely unique way. I notice that you are the same as u. So this is what I'm going to do. I'm going to build a parentheses with an invisible 1 right there. On the bottom, I'm going to build a parentheses with that 3 that was already there. In this parentheses, I have 2m to the negative fourth, and I have 2m to the negative fourth. Notice these guys are the same. If you have something in parentheses that's the same thing as something in the parentheses down here, you're allowed to simplify. So I have 1, 2m to the negative fourth in the numerator, and I have 3, 2m to the negative fourth in the denominator, which means there's 2 more in the denominator. So that's going to be 2m to the negative fourth. Now I'm not done yet. What I need to do is I need to distribute that 2, so you're going to become a 1. So if I were to distribute that 2, 2 times 1 is 1, so 1 on the top still stays there. 2 times 1 is 2, so 2 times 1 is 2. M to the negative fourth times 2 is going to be m to the negative eighth. I can clean this up a little bit more. 1 is still 1, but you know what? I'm going to not write it there. 2 squared is 4. M has a negative exponent. If you have a negative exponent, move it to the other side of the fraction bar and make it positive. So when all is said and done, this guy becomes m8 over 4. Now this is the way that I did it. That's not the only way that you can do it. If you decided, oh, I'm just going to distribute the 3 and then move things around, that's perfectly fine. Perfectly fine. I just noticed something and I went on a different tangent, and so I had fun with it, and that's what I get. The same answer no matter what you do, as long as you do it right. Simplify in parentheses 2x to the third z squared, all of which to the third power, all over x cubed, y to the fourth, z squared, times x to the negative fourth, z to the third. All right. Lots to do, lots to do, lots to do. First things first, I have a parentheses taken to an exponent, and inside the parentheses, I have a bunch of stuff going on with exponents too. What I want to do is label all the exponents. So yes, I'm going to put an invisible 1 there. When you take a parentheses to an exponent, you distribute that exponent to every exponent here and multiply the exponents. So 3 times 1 becomes 2 to the third. 3 times x to the third becomes x to the ninth, and 3 times z squared is going to be z to the sixth. Now downstairs in the denominator, I have x to the third and x to the negative fourth. Let's group those together. X to the third, x to the negative fourth, right? I have y to the fourth and nothing else like it, so y to the fourth. Z squared and z to the third, let's group those. Z squared, z to the third. Now looking at this, what I see is I see 1 and only 1 negative exponents and a fraction bar. Go through all 1, 2, 3, 4, 5, 6, 7, 8 terms of this and see if your term stays or moves depending on whether it has a positive or a negative exponent. If it's a positive exponent, it stays. 2 to the positive 3 stays. X to the positive 9 stays. Z to the positive 6 stays. X to the positive 3 stays. X to the negative fourth moves to the top and becomes x to the positive fourth. Y to the fourth stays. Z squared stays. Z to the third stays. Now if you want to, you can rewrite this, and maybe I will, so that things are next to each other. So I notice that I have an x to the ninth and an x to the fourth. Why not scooch those next to each other? Because why not? Leave the z6 there off to the side where it belongs. I have x to the third, y to the fourth, z to the second, z to the third. If you have terms of the same base next to each other, deal with that first. 2 to the third is 2 to the third, leave it for now. X to the ninth times x to the fourth are terms of the same base. If you're multiplying terms of the same base, add the exponents, x to the 13th power. Z to the sixth, z to the sixth. X to the third, x to the third. Y to the fourth is y to the fourth. Z squared times z to the third are terms of the same base that are being multiplied together. Add the exponents and make it z to the fifth. Now we're not done yet, because I have x's upstairs and downstairs and z's upstairs and downstairs. 2 to the third is 2 to the third, leave it there. I have 13 x's in the numerator and 3 x's in the denominator. Whenever you have terms of the same base, right, and you're dividing them, find out which one's more powerful. X to the 13th is more powerful than x to the third. Leave it in the numerator, subtract the exponents, and call it 10. Okay? Similarly, I have z to the 6th power up here and z to the 5th power in the denominator. 6 is barely more powerful than 5, so leave z up there, and 6 minus 5 is invisible 1. Now you just have this y kind of living down here all by itself, so leave it. So let's clean this up a little bit, and I'm going to write this out 2 different ways because it all depends on your teacher and how they accept this. 2 to the third can stay 2 to the third for now. X to the 10th is x to the 10th. Z to the invisible 1 we'll just call z. Y to the 4th is y to the 4th. Many teachers would be like, that's perfectly fine. But a lot of teachers might be like, I don't know, 2 to the third, isn't that 2 times 2 times 2? And if your teacher's like that, you would just be like, all right, 2 times 2 times 2 is 8. So 8, 10 to the third, z all over y to the 4th. Both of these are the same exact thing. Both of these are acceptable. It all just depends on what you're trying to do and what curriculum you have. But at the end of the day, we end up with those answers, and neither one of those is technically correct. Write the number in scientific notation. Whenever you take a number in standard form and write it in scientific notation, what you have to do is you have to move your decimal so that you have just one digit between 1 and 9 up front. So my decimal is supposed to be here. So it's 6.0 times 10 to the something power. Now this is a very small number. Okay, it's a number smaller than 1, which means the exponent's going to be negative. What number do I attach to it? Well, that's all dependent on how many decimal places you move. 1, 2, 3, 4, 5, 6. So I put my dot after the 6. I moved 6 times, and since this number was less than 1 to begin with, it was 10 to the negative 6. That is how you write that number in scientific notation. Write the number in scientific notation. In order to put a number in scientific notation, you have to place a decimal so that the first digit is a 1 digit only. So if I put a dot between 5 and 4, I get 5.4. That number is in between 1 and 9.99999. I'm good. Now this is a larger number, bigger than 1. So what I need to do is it's going to be times 10 to the positive exponent. How do I find the positive exponent? I move my decimal place to the other decimal. So there's an invisible decimal there at the very end, and it's a change of 1, 2, 3, 4, 5, 6 spaces. So this guy becomes 5.4 times 10 to the 6. Write the number in scientific notation. Well, in order to write a number in scientific notation, I have to make sure that my number is a 1 digit only, and then anything else after that is anything else after that. Well, that is 1 digit only. So it's going to be times 10 to the something. So in order to turn 6.7 to 6.7, I don't move my decimal at all. So what number goes here? 0. So that's technically scientific notation. Fun stuff. Write the number in scientific notation. We're given 33 times 10 to the negative third. Now you might be looking at that saying, that is scientific notation. 33 is too big for it to be scientific notation. So let's focus on the 33 first. If I wanted to turn 33 into scientific notation, I would place the decimal in between the 3 and 3 so that's 1 digit and 1 digit only. So it's 3.3 times 10 to the. This number is bigger than 1. Okay, it's bigger than 10. So what I want to do is I'm going to have a positive exponent here, and I have to figure out how many decimals I would move. Well, the original decimal was there, and I created that decimal right there, and so it's a change of 1. So this becomes times 10 to the first. Now, what about this times 10 to the negative third? That's just lingering. Well, it is. It's just lingering. Now, 3.3 is 3.3. When multiplying terms of the same base, you add the exponents. 10 to the first times 10 to the negative 3 has me adding 1 and negative 3. So this becomes times 10 to the 1 plus negative 3 is negative 2. Now, you might be thinking, should we move that to the bottom of a fraction bar? Nope. In scientific notation, you're allowed to have negative exponents. So we're going to leave it like that. That's going to be our answer. Write the number in standard notation. When you take 0.9 and multiply it by 10 to the negative 1, you're going to make your number smaller because 10 to the negative 1 makes things smaller. So you take your decimal and you move it to the left however many spaces it tells you to. So you're going to move it to the left 1 and put your new decimal right there. So this ends up becoming 0.09. And I'm just going to put a 0 in front of it because it looks prettier. And that's how you do it. Write the number in standard notation. Whenever you're taking a number and multiplying it by 10 to the positive exponent, you're making that number larger. How much larger? Well, it all is dependent on that number right there. We're going to take our decimal, and the way we make a number larger is by moving our decimal to the right 7 times in this case. So 1, 2, 3, 4, 5, 6, 7. Now we have all these open spaces. Fill them in with zeros, like so. So 9, 5, 0, 0, 0, 0, 0, 0, put a comma, and you have 95 million, which is how much money I make in a month. I'm just joking, not even close. Like and subscribe. Write the number out in standard notation. When you take a number and write it out in standard notation, what you do is you have that number, write it out. You identify where the decimal is, so there's an invisible decimal right there. And since we're multiplying it by 10 to the second power, we're making our number larger, which means we're going to move our decimal to the right that many times. So 1, 2, put a new decimal there. Fill in all blank spaces with zeros. And so we end up with 8, 0, 4, 0, 0. Put a comma there. Circle that up, and you're done. Write the number in standard notation. Whenever you're taking a number in scientific notation and writing it out in standard notation, you take that number and you just write it out. You put a decimal where the decimal is supposed to be, and you move it depending on how many places it tells you to move it in that exponent. Well, that's a 0. So where are we going to move our decimal? Nowhere. So this just becomes 4. Now this should make sense. Anything to the 0th power is 1, so 4 times 1 is 4. Easy peasy. Simplify. Write the answer in scientific notation. All right, well, we have 2 times 10 to the negative 4th times 8.1 times 10 to the negative 1. Now notice the way I said it. I said 2 times 10 to the negative 4th times 8.1 times 10 to the negative 1. I don't want to use the x. I want to be consistent with my dots, like so. This is the same exact thing. You're just multiplying straight across. So the parentheses here are just grouping things. Move the 2 and the 8.1 next to each other. So 2 times 8.1. More importantly, move the 10 to the negative 4 and the 10 to the negative 1 next to each other. So times 10 to the negative 4 times 10 to the negative 1. 2 times 8.1 is 16.2. When you multiply terms of the same base, you add the exponents. So negative 4 plus negative 1 is negative 5. However, this is not scientific notation because 16 is too big. Our decimal should be here. So in order to take 16.2 and make that guy scientific notation, we write it out as 1.62 times 10 to the positive 1. Now I have 1.62. When multiplying terms of the same base, add the exponents, so times 10 to the negative 4. So a little bit more work than we're used to, but that's how you do it. Simplify. Write the answer in scientific notation. All right, so we have ourselves 3.48 times 10 to the third times 9.8 times 10 to the fourth. Let's write out 3.48 and 9.8 next to each other because I can. If all we're doing is just multiplying everything, no adding, no subtraction, just multiplying, you're allowed to move things together. Let's move the 10 to the third next to 10 to the fourth. 3.48 times 9.8 is 34.104. Okay, so yeah, you're going to want a calculator probably for that. 10 to the third times 10 to the fourth, when multiplying terms of the same base, add the exponents. So this becomes 10 to the seventh. Now, if you're thinking, now it's in scientific notation. No, it's not. 34 is too big. So you need to put the dot right there and call it 3.4104. Since this number is larger than 10, it's going to be times 10 to the positive exponent, and that positive exponent is just going to be a change of 1. Okay? 10 to the 7th is still there. So to finalize this problem up, we have 3.4104. 10 to the first times 10 to the 7th has me adding the exponents, because when you multiply terms of the same base, you add the exponents. So times 10 to the 8th. Now we're in scientific notation, and now we are done. Simplify. Write the answer in scientific notation. 7.1 times 10 to the 6 over 8.2 times 10 to the first. All right, what we're going to do is we're going to probably use a calculator and simplify this guy first and see what we get. So let's type that into our calculator off to the side. All right, according to my phone, you get 0.8659. Fun. Now, whenever you divide terms of the same base, you figure out which side is more powerful, the top one, and then you subtract the exponents. So 6 minus 1 is 5, so times 10 to the fifth. Now, before you get all antsy and say, now it's in scientific notation, no, it's not. My number here is supposed to be in between 1 and 9.99999. So I have to put a dot between 8 and 6 here. Since this number was less than 1, this becomes 8.659 times 10 to the negative exponent. Since I moved over 1, it's going to be 10 to the negative 1, and then multiply that to 10 to the fifth. So 8.659, let's multiply these guys together. When multiplying terms of the same base, you add the exponents, so times 10 to the fourth. And that's going to be our guy. Simplify. Write the answer in scientific notation. All right, so we have 9 divided by 9.24. Let's do that guy first, see what Mr. Calculator says. All right, 0.974 is what it said. And now we have this. Okay, we have 10 to the negative fifth over 10 to the negative 6. Okay, now I want to keep everything in scientific notation upstairs in the numerator, so I want to keep it next to it. So what we have to do is, if you divide terms of the same base, subtract the exponents. So in my head, I'm doing, all right, let's leave negative 5 up top, minus negative 6. So in my head, negative 5 minus negative 6 is a double negative, so negative 5 plus 6 is invisible 1. Not so bad. And if you think you're done, I have terrible news. You ain't. This number is way too small. Not way too small, barely too small, actually. I'm supposed to have a decimal between the 9 and the 7 because I'm supposed to have a 1 digit in front here. So since this number was less than 1 to begin with, I now have 9.74 times 10 to the negative. That negative is going to be negative 1 because it's a change of 1. That 10 to the first is living out here. Now, when you multiply terms of the same base, you add the exponents. So 9.74 times 10 to the negative 1. Negative 1 plus 1 is 0. So this just becomes 10 to the 0. And that's going to be our guy. Kind of a weird, ugly, gross problem, but we did it. Simplify. Write the answer in scientific notation. All right, so I have 8.9 to the invisible 1 times 10 to the 5th, all taken to the 4th power. Take that 4 and multiply it to both of those. So now you have 8.9, 1 times 4 is to the 4th, times 10 to the 5 times 4 is to the 20th. Now let's go off to the side and find out what 8.9 to the 4th is. And according to my calculator, we get 6274.2241. And that's going to be times 10 to the 20th. Now, this is not scientific notation because that number is way too big. There's supposed to be a decimal in between the 6 and the 2. This number, since it's too big, is going to be 6.2742241 times 10 to the positive exponent. What's that exponent? Well, to get from one decimal to the next, it's going to be 1, 2, 3, so 10 to the 3rd. And that's going to be living next to the 10 to the 20th that's already there. Now, this gross number is just that gross number, can't do much about it. So let's just write it out. 10 to the 3rd times 10 to the 20th is 10 to the 23rd, because you add the exponents. Simplify and write the answer in scientific notation. I have that parentheses right there taken all to the negative 6 power. So 6.3 to the invisible 1 times 10 squared to the negative 6 power, all of which. Take that negative 6 and distribute it to both. So now you get 6.3 to the negative 6 power times 10 to the negative 12th power. Now you're definitely going to need a calculator to find out what 6.3 to the negative 6 power is, so let me go off to the side and do that. 0.00001599, not the prettiest guy on the planet, but that's going to be multiplied to 10 to the negative 12. Now, this is not scientific notation because that number is way too small. There's supposed to be a dot in between 1 and 5. So since this is a small number smaller than 1, we are going to write out, I don't need all these zeros, 1.599 times 10 to the negative. And again, it's a negative because that number is smaller than 1. Negative what? Well, let's find out how we get from one decimal to the next. 1, 2, 3, 4, 5. So 10 to the negative 5th. And then that times 10 to the negative 12th is still lingering out there. So now what we have to do is we have to combine these guys. So 1.599 is still hanging out there. When you multiply terms of the same base, you add the exponents. So negative 5 plus negative 12 is negative 17. And that's going to be your guy. Not the prettiest, but that's how you do it. Simplify and write the answer in scientific notation. All right, first things first, that's a plus sign. So what we have to do is we have to follow PEMDAS and actually multiply these guys out. So if I wanted to do 3.1 times 10 to the 3rd, that would be moved to the right 1, 2, 3 because you're making it bigger. And so 3.1 times 10 to the 3rd is 3,100. Okay, this guy is going to be 4.3 times 10 to the 3rd. So also move that to the right 1, 2, 3 times and put your zeros there. And so now we add that. Let's add these numbers the way you normally would. Okay, 3,100 plus 4,300 is 7,400. And now I can turn that into scientific notation. Put a dot in between the 7 and the 4. So 7.400 is just 7.4. That is a number larger than 10, so it's going to be times 10 to the positive. And it looks like to get from one decimal to the next, you move to the right 1, 2, 3, so times 10 to the 3rd. So definitely not the prettiest problem, but also not the craziest either. You just have to be careful that that is a plus sign, not a times sign. So you just have to make sure that you're using PEMDAS and not just moving things willy-nilly. You don't want to move things willy-nilly. Simplify. Write the answer in scientific notation. This is going to be gross. All right, so we have that number right there, minus a different number right there. This is minusing. not timesing. So you can't just move things around because of that subtraction. We have to follow PEMDAS. So we actually have to do the math here. So let's do 2.74 times 10 to the negative 1 has me move my decimal place to the left once because it's getting smaller. So you become 0.274. Over here, you have 6.53, and you're also making this number smaller because you're moving it to the left 1, 2, 3, 4 decimal spaces. So you become 0, 0, 0. So you become 0.000653. Now we're going to subtract these two, so this is going to be awful, 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 awful. So according to Little Miss Siri, you get negative 0.2733. I'm going to trust her. Right? And so that's the number that we get. Now, if you look at that, that number is way too small. So what we have to do is make sure our decimal is right there in between. So since this number, the digit itself is less than 1, we move it over 1 here. That becomes negative 2.733 times 10 to the negative first. So definitely not the easiest problem. These problems are pretty gross, especially when that's a plus or a minus, but that's how you would do it. Simplify and write the answer in scientific notation. That's a minus sign in between, which means we have to follow PEMDAS and deal with the multiplication stuff individually. So let's do that. Let me write this out as 5.9 times 10 to the negative 2 means I move my decimal place to the left 2 times. So that leaves me with 0.059. Okay. This guy has me putting 0.078 and moving it to the right 1, 2, 3 times. So you become just 78. So now I end up with 0.059 minus 78, which becomes negative 77.941. That number is too big. I'm supposed to have a dot in between the 7 and the 7. So that becomes negative 7.7941. Since I moved over 1 and that number, the digit itself, and yeah, I see the negative there, but the digit itself is greater than 10, that's going to become a positive exponent, so 10 to the first. Gross, but we did it. The diameter of Earth is approximately 1.27 times 10 to the fourth kilometers, while the diameter of Jupiter is approximately 1.43 times 10 to the fifth kilometers. How many times larger is the diameter of Jupiter compared to the diameter of Earth? We need to find out how many times bigger Jupiter is than Earth. So we're going to divide Jupiter over Earth. That's how we're going to do it. So Jupiter was 1.43 times 10 to the fifth. Earth is 1.27 times 10 to the fourth. Okay, these guys are like terms, so divide them. You're going to need a calculator, and you get approximately 1.126. When you divide terms of the same base, subtract the exponents, so 5 minus 4 is 1, so times 10 to the first. Now, fortunately for us, that is in scientific notation. That rarely happens. When we do all of this, your answer actually ends up in scientific notation. So we can say 1.126 times large. Oh, no, that was a close one. Times 10 to the first times larger. Well, that was a close one. But we did it. The Sahara Desert is estimated to contain approximately 9 times 10 to the 21st grains of sand. How biblical. A typical beach is estimated to contain about 5 times 10 to the 18th grains of sand. How many times more grains of sand does the Sahara Desert have compared to a typical beach? So what we're going to do is we're going to take the Sahara Desert divided by a typical beach. Let's go to the beach each. Nicki Minaj. Sahara Desert, 9 times 10 to the 21st. The beach, 5 times 10 to the 18th. Divide those like terms. 9 divided by 5, I'm pretty sure, is 1.8. When dividing terms of the same base, subtract the exponents. 10 to the 21st minus 10 to the 18th is going to be 21, 9 plus 10, minus 18, which is times 10 to the third. And fortunately for us, this is scientific notation already. So we could say, how many times more grains of sand does the Sahara Desert have compared to a typical beach? 1.8 times 10 to the third times more. Bada bing, bada bang, bada boom, bada pow. Oh, that should do it for this volume. Thanks for watching.